Okay, so we are concerning about something called viral marketing, right? You have this social network connecting people, and then suppose this Mary is the sender, he posted some message, and this piece of message will diffuse across the social network. But after some time, this message reaches a certain number of people. Okay, so as an advertiser, you want to make use of this type of information diffusion. So, for instance, if you put some advertisement on some user in the social network, you want to have as many people to see this advertisement, and you want it to diffuse across the social network as much as possible, for instance. Okay? So in this domain, the question we can ask is, the first thing is how do we actually accurately estimate the extent of the spread of the information? Suppose that you want to answer a question like this. If you release a piece of information to a few users, can this piece of information spread to 1 million people within a month, for instance? And then actually the time horizon attached to this question is very important. As an advertiser, you don't want the advertisement to spread to 1 million people in a year, but you want it to have such spread in maybe just a month. Okay? And then the second thing is the advertiser has only limited budget. He can only select a small number of users to spread information. Then how do I choose this small number of users wisely, such that I can get the most out of it? Usually this kind of questions are conducted in a huge social network. You have millions and billions of users, and you want to have a very efficient algorithm to be able to estimate this. Okay? So basically you want to answer this question in a time-sensitive fashion, and then want it to be very scalable. So traditionally, when people try to model this type of information diffusion, they used something called, usually use this kind of discrete diffusion model. Here is just an example for this type of diffusion model called the discrete time independent cascade model, originally proposed in David Kemp 2003 KDB paper. Okay, so this process is very simple. So you just have this social network. Suppose you have a directed network. Okay, the information can only spread from the parent to the child. Okay, so and this kind of diffusion process spread in rounds. In the first round, maybe node J is infected as the source node, and then you go to the next round, and then each one of these node is going to be infected by its parent with some fixed probability. Okay, if you have edge connecting J and I, then this J node, if it's already infected, it's going to infect each child with probability, fixed probability each one. For instance, in this particular example, in the second round, none of the additional nodes are infected. But if you move to the third round, there may be another node infected. Then once there are two nodes infected, they're going to directly infect the downstream neighbors. And then you go to the third round, then maybe more nodes get infected. Okay? This is the one very, very popular diffusion model. But this diffusion model somehow has some mismatch with reality. First, in reality, the information spread is actually in continuous time. Okay? And in order to feed such a discrete time diffusion model to your data, you have to first discretize your domain, okay, discrete your time, and turn it into rounds, and feed such a discrete model. And then there will be a question of how large is this time window you use to discretize your time domain. The second thing is if you do it, model it with this kind of discrete time independent cascade model, you associate with each edge a fixed something like infection probability. Effectively, you will be only able to model this diffusion in a very restricted set of models. So what we're going to do is, once you have such a diffusion model, if you look at a reality like the information spread is really, suppose I have some initial source node, the information really spreads in continuous time. You can see people getting infected, because in this particular case, the infection means just people retweet about something. Okay? At any time, the y-axis is just each row is about user. Okay? And then it's very hard to just find an appropriate time window, which you feed this discrete time diffusion model. So what we're going to do instead is to use a continuous time diffusion model. Okay? So the differences between continuous time diffusion model and discrete time diffusion model is, the first thing we're going to associate each one of the edge. Instead of a fixed probability of infection, I'm going to associate it with a density over over the infection time. It is effective a conditional distribution, conditional density of node I being infected, given the parent node Tj is infected with a Tj. Okay? And again, each node is going to be infected by its parent independently. So instead of infecting this node in rounds, we are going to sample a time, okay, for each one of these from this kind of conditional density associated with the edge. And if a node is infected, it stays infected. So the example is something like this. Suppose at time 0, node J is infected, and it's going to infect downstream node according to the associated conditional density on each edge. We draw some random samples. Okay? Suppose in this particular time, the random sample for K is Tk. Now J and K are infected, then they're going to directly influence the downstream node L and I. And you also draw some kind of random samples, okay, for the time. But now TL is, L is infected at time TL. And then they directly influence I, it's going to be infected at TL. Okay. So it's such a model. Based on this diffusion model, you can actually write out the joint density for this set of infection time for each node. Okay, you can basically sample from this distribution, you get a bunch. Each time you sample, you get a different set of infection time for the nodes. So an alternative way to view this diffusion model is something like this. Okay? So essentially, the conditional density is associated with each edge. You can think about you can sample a time for each one of the edge, and every time you sample the edge, essentially it's like a network with fixed number of nodes, but the length of the edge is changing. Okay, the length is going to correspond to the time. Okay, and then the length is just the difference between the two infection times. And then once you sample a set of random edges, then the infection time node I is going to just be the shortest path between the source node and this particular node. So the process is something you first independently sample and add edge weights, and then you find the shortest path. And that shortest path is going to give you the infection time. So suppose you sample another set of edge weights, you get a different configuration of network. And then infection time is shortest path, that shortest path. It's going to be a different infection time. Okay? So the wheel in the last slide and this slide are equivalent. And actually, what we're going to do for designing a very efficient algorithm is going to exploit this dual wheel of this infection algorithm. Okay? So the first thing is we try to maximize the inference. We are going to define this quantity of what do we mean by inference in this continuous time diffusion model. So what we mean by inference of set of nodes A in the network in the time window between 0 and t is going to be the expected number of nodes that is infected before time t. So each one in the node is going to associate with the infection time random, this random variable. So we just check for each node whether it's infected before time t, the infection time whether it's smaller than t or not. If it is smaller, it's 1, otherwise it's 0, and then you take the expectation with respect to your diffusion model. Okay? In this case, we assume the diffusion network structure and diffusion model are given. Okay? So you just want to compute this expected value if you want to estimate inference. So an equivalent expression for this definition of inference is you can actually exchange the summation and expectation because that's a linear operation. And then the inference is actually a sum of the probability for individual node that is going to be infected before time t. Okay? So once you are able to compute this, so an inference function, then if you want to maximize the inference, effectively you are just solving, you are trying to solve a discrete optimization problem. You try to select a set of node A with size smaller equal to C, such that this inference is going to be maximized. But and this function has some nice property you can prove about it. It is non-negative and non-decreasing submodular function. You can use a very greedy algorithm to solve it and obtain a solution which is very close to the optimum. But the The catch is, in order to run this optimization problem, you will need to have a very efficient way to evaluate this objective function under this diffusion model. So one way you can do is, of course, compute that probability exactly according to the diffusion model. So I already assumed that you are given this diffusion network and then the corresponding parameter associated with this diffusion model. So you can compute it. The catch is it's very expensive to compute the objective function. So what we're going to do is to have a very efficient randomized algorithm to compute this objective function, allow you to do this maximization in a very efficient way. Okay? So why is it so difficult to compute that objective function directly? So we have this diffusion model. Effectively, we have defined a joint density for this collection of infection time. And it's actually highly related to a directed graph model where you have a bunch of factors brought together. Each factor is going to be the conditional density of the infection time of I given the parents. Okay? So if you want to compute the probability of this infection time for I smaller than t, effectively you need to marginalize out all other variables that is not here. Okay? You want to integrate out to many variables, continuous variables. So it's a very difficult inference problem in graphical model. So we want to avoid that. So what we do is to go through this route of this dual wheel of elastic network. So we're going to basically approximately estimate this quantity by using a set of samples from this elastic network. Okay? So what we're going to essentially do is we sample a bunch of networks. For each one of these sampled networks, we are going to compute this quantity or estimate this quantity, the number of nodes that is infected before time t. And then we sample another network and estimate this again, and we sample n networks. Then we use the final sample average, approximate it. It feels like the story ends here, okay? You can just sample a network, do this computation, and you get an estimate. But it turns out that if you want to do this explicitly, and then plug it into the inference maximization greedy algorithm, you're going to get a computation which is quadratic in the network size. So we want to avoid it. We want to be linear in the size of the network, essentially. So how do we do that? So the first thing is, let me just reiterate a little bit this elastic network kind of wheel. So you have this diffusion network structure is given to you, but for each edge you have a conditional density over time associated. You sample this kind of network, and then to basically compute the number of nodes that is infected before time t. A very simple way you can do it is just to run shortest path algorithm. You check for each node, you run shortest path, and then see whether the shortest path is smaller equal to t or not. Okay? And then you sample another node, and you check for each node whether the shortest path is smaller equal to t. You need to do it, yeah.
So you observe the times, right? But you don't observe the network. Your data is
so I assume the network structure is given to you, and then also the parameter associated with the edge is given to you.
Like a parametric form that you can sample from?
So as long as you can sample it from, it's one-dimensional density, by the way. As long as you can sample from this one-dimensional density, then you will be able to do this algorithm. Okay.
So you know the connections?
Yeah.
Okay.
So actually in the experiment, we have a different paper about estimating the structure and estimating the parameter using some kind of convex optimization. But in this paper, it's just about inference once you have the model. Okay. So if you are going to run just shortest path and compute that quantity explicitly, and basically for each source node you're interested, you fix a source node, you want to estimate the number of nodes that is infected within T. The computation you're going to get is going to be linear in the number of edges and nodes. But in the inference maximization algorithm, you need to check for each node as the possible source. And then immediately give you some algorithm quadratic in the number of nodes in the network. So you want to avoid it. Okay. So what we do, instead of basically computing this shortest path, we are going to turn this problem into a problem of estimating the so-called neighborhood of a node in the So this M denotes the neighborhood of the number of nodes within distance t. This whole quantity, we're going to denote it as NJT, okay? Suppose J is the source. We are going to, instead of using this shortest path to count it exactly, we are going to use a second level of randomization to estimate this quantity. Okay? So basically, we are going to try to estimate this count. Okay? You sample network, I'm going to estimate this count rather than compute it explicitly. You sample not network, I'm going to estimate this count. Okay? So how do we estimate? We are using an algorithm actually dates back to 97, coming from theoretical computer science literature. So the intuition of this algorithm is using a very special property of the exponential random variable. If you have a set of m, suppose, exponential random variable R1, R2, up to Rm, and each one are drawn independently from some exponential distribution. Then if you compute the minimum of this m exponential random variable, it's going to distribute it according to exponential distribution, but with parameter change to m, okay? So suppose that you're given a bunch of these R star random variables. Then I can estimate the parameter of this distribution with the maximum likelihood. So it's effectively this estimate, suppose I'm given a set of R star, I'm going to just estimate this m with this quantity. Effectively, it's the sum, is the average of these R stars, and then take the reciprocal. Okay? And the n minus 1 is just to carry out some of the bias. It becomes an unbiased estimate. So the key idea to make use of this type of property of exponential random variable is you generate some kind of random labels for each node in a network. And I'm going to find for each node the R star. Okay? And then that's going to, if I have a bunch of this R star, it's going to give me an estimate of the neighborhood size of the node, okay, using the properties. So basically, we are going to basically, for each fixed network we draw from this elastic network, we are going to sample, according to the exponential distribution, a label for each node. Okay? And then for source node J, suppose we are interested in this source node J. We can find the smallest R star within distance t, right? This is, okay? So suppose in this case, this length is much larger than t. And then the smallest label within distance t is going to be 0.2. You're going to record it. R star for J is 0.2, okay? This is no different from the shortest path algorithm. So a clever algorithm is actually first build some data structure to pre-process your network structure. And it's a little bit like a prefix and suffix tree type of algorithm. You're going to do something very similar to suffix tree. So the way you do it is, what you're going to do is, you're going to, the same thing you do is you draw a bunch of exponential random variables. Then now, you start from the smallest label. You traverse the graph in a backward fashion, okay? And then up to distance t. As long as you see some nodes, within this node, for instance, in this case, the length of these edges distance t, okay? So within distance t, it only hits that node. I'm going to recall in this arrow, this smallest label, 0.1. Okay, then I'm going to move to the second smallest label, 0.2, and then do this backward traversal. Okay, as long as I hit some node, I'm going to record it, the minimum label. Okay, so this way, you basically first saw this smallest label, and then you traverse according to this order. And in each node, once it hits a node, you just record it, the particular label. Okay, you pre-process just this. This can be done in time linear in the network size. Okay? So with this, then you will be able to essentially query. So query for instance, if my source node is this one, if I want to query what is the smallest label I can reach on constant time. If you want to query this one, you can essentially achieve the query also in constant time, because I do this order linear processing, and then keep that data structure. When I query it, every time it's constant. That's how I achieve the overall kind of linear algorithm. So overall, the algorithm is going to be like this for estimating these. So you're going to sample n random networks. Okay. So for each network, you're going to sample a bunch of exponential random variables. Okay. And then for each one of these sample exponential random variable, you're going to basically build this data structure. And then this is pre-processing. We haven't talked about querying any nodes yet, because in the inference maximization, you need to query this. So you use essentially this one is linear in the network size. Afterwards, if you want to query a particular one, what I'm going to do is I go to the particular node and retrieve the corresponding R star, and apply this formula to estimate the inference. So this is about estimating the inference for an individual node, but if you have multiple nodes as a source, you can just do a very small operation, also constant time operation, to estimate inference as well. Basically by taking the minimum of the minimum, you get a, yeah.
So n is not the number of nodes in the network, n is just the number of samples, correct?
Yeah.
Okay.
This n is the number of samples.
Yeah, so do you have some relationship between n and the number of nodes in the network?
The relationship, you mean the computation, intensive computation?
I'm saying some bound on the number of samples n I need. Does it grow with the number of nodes in the network?
It actually grows according to the diffusion sort of dynamics. If the diffusion is very fast, so you actually need more sample to estimate it more accurately. We had a bound for this. It doesn't depend on the actual network size. Okay, only for computation it is going to depend on the network size. So in terms of computation complexity, it's really basically you have n random sample for the networks, and once you have this n random sample network for each one network, you have n randomizations, and you get this data structure in linear time in the network size, and you times these random randomizations. Okay, and when you want to query the inference for each individual node, you can shift this query in essentially time just proportion to the number of randomizations. So it's independent of the network size. So the overall computation complexity is the first level of randomization times the second level of randomization, and the linear in the number of edges and nodes. So with this algorithm, essentially you will be able to estimate the objective function for this optimization problem very efficiently. And this allows you to basically do this greedy algorithm when there's millions of nodes in the networks. Okay. Since we are not calculating the objective function exactly, we're just estimating it. So every time we're going to introduce some errors in the function value, and then with this additional error epsilon, so we can actually guarantee that if you solve this optimization problem with an approximate function evaluation, you will obtain some solution which is pretty close actually to the optimal. It's just have some additional additive error in the guarantee. Okay, so we have done lots of simulations that showing that this randomized algorithm is actually able to estimate this objective function very accurately. And then when you maximize with that in the simulation data, you also get much larger, basically, inference. I'm not showing that, I'm just showing the scalability of the algorithm. Okay, I'm going to show you the real world experiments in terms of maximizing the inference. In terms of the scalability, we basically, compared to other approaches, most of these inference maximization algorithms either based on exact evaluation of the objective function, it's just not scalable. Okay, it cannot be scaled to maybe 1,000, even 1,000 nodes. So we are doing experiment to the scale of 1,000,000 nodes. Okay? So, but first let's look at just 100 nodes, comparing the sampling approach, a randomized algorithm, to the algorithm where you actually use shortest path for the computation. Okay, computing still the objective function exactly. So you get 2 orders of magnitude improvement in terms of computation, and then doesn't matter you increase the number of sources you are interested, and then even you increase the number of edges you are interested, okay? And then you still get this 2 order of magnitude speed up. And then for this purple line, which is for some algorithm based on analytic solution under very restricted setting, it's essentially take more than 24 hours, even for a network of size 128 nodes. When it is up to 1 million nodes, our method is able to finish, actually, we set upper bound for all the experiments, 48 hours. If a method doesn't finish in 48 hours, we just stopped. And then for this approach-based and shortest path, trying to compute this objective function exactly, they just cannot scale up once you have more than 10,000, okay? 10,000 nodes. So in terms of the river data set, we actually use this checker data set, which is about information diffusion across different block spaces. So what we are going to do in this case is we are actually using 80% of this cascade data, okay, actual information propagation, to learn the diffusion network structure and also the diffusion parameters. And then we are using this learned model to basically maximize the inference using our approximate algorithm. And then once we do that, we're going to evaluate this, how good the selected nodes are using the remaining 20% of the cascade. We see that we are going to identify this 20% cascade, those nodes starting with the source I selected, and see what is the actual inference. So if it's larger, then you select root source nodes. So the first thing is we can actually compare the estimate inference for each individual node and the actual inference of individual node. So the difference, the smaller the better, okay? So we can also look at the difference when we vary the time horizon of interest, okay? Across a range of different time horizons, our method for estimating this inference is much more accurate than many other methods based on diffusion, a discrete time diffusion model. Okay? So when we use our method to select the sources and trying to maximize inference, again using the same evaluation scheme, you increase the number of sources, and compared to other methods, our method is always achieving much larger inference. So the same thing you can do is vary the time horizon, okay? And then you fix a sort of selected node, and then the inference achieved by our method is also the best. So this is basically a summary of the experiment. There are much more experiment in the paper. You can go and read it. So, but I would like to just summarize what is in this algorithm. It's a very simple randomized algorithm, 2-level of randomized algorithm. The first level of randomization is going to draw a set of sample from this elastic network. And the second randomization is going to basically, for each fixed random network, you are going to estimate the number of neighbors for particular nodes within this scheme. Okay, we're not going to compute exactly. We're going to use randomizing algorithm to estimate it. And if you put these two things together, you actually get a very good estimate of the inference. Okay, and then with this method, you will be able to scale out this submodel optimization problem to millions of nodes. Without that, it's just impractical. Okay. So there are many other interesting questions and randomized algorithm can do in this context. So I just described a very specific diffusion model, continuous time independent cascade model. Okay? There are many other diffusion model you can use and study how do you actually maximize the inference. Of course, I'm talking about selecting the nodes to maximize inference. But you can also think about problem. You try to change the network topology. And either you want to remove some of the edges in the diffusion network such that some epidemics is going to be contained. Okay? Or you want to add a few number of edges in the network such that a particular type of information can spread as fast as possible. Okay, there are many questions in the domain, and then you want to do it in a large scale, then randomized algorithm is the method of choice. That's it. Okay. You have any question?
Yeah. Okay, so a different problem would be to ask